Previously, we used the return value of a function to pass the address of memory allocated on the heap back to the calling function. But we may want to use a function's return value for some other purpose. Or perhaps we simply prefer to alter a pointer in the calling function. Whatever the reason, it's important to know how to use a parameter to store the address of dynamically allocated memory.
Here we have a C function that dynamically allocates an array of 3 integers on the heap and assigns values to those integers. The address of that block is assigned to a local variable r. When the function returns, the data will still be allocated on the heap. So to continue using the data, and to avoid a memory leak, we need to retain a copy of the heap address. In the past videos, we returned the value of r to the calling function and assigned it to a local variable there. This would mean making the return type of helper int star and adding the return statement. We return the value of variable r. And here is the calling code from main. We assign the return value of our function to the local variable data. Another approach is to use a parameter to our helper function to store the address of the array on the heap. First, we change the return type, since we aren't going to use the return statement for the address in our malloc space. Now it's free for other uses, like signaling an error, although in this example, we simply won't return anything at all. The value we would like to get back to our calling program is the address of the array, the value of r. That's what we returned in our earlier version, and the type of r is int star. Here's a common mistake. It would be a mistake to make the parameter int star, but let's try it. And now let's call the function in main. What do you think we'll see when we run this code? If it had worked, we would have seen a 21, but we see a 0. Why? Remember where this is allocated. R is a local variable on the stack of the helper function. When we call helper, it gets the value of data. But when we modify R, we're modifying a local variable, not the variable data from main. The visualizer highlights this. R is being changed, but data is not, and we want to change the pointer data. This means we need a parameter that allows us to change the pointer. So our parameter should be of type int star star. We'll pass the address of data rather than the value in data. Then, when we allocate the space for the array, we're modifying our original pointer from the calling context main rather than a local variable. For convenience, so we don't have to dereference our parameter everywhere, we'll create a local variable that stores a reference to the array. Now we get the value we expect. And using the visualizer, we can see that when we store the return value of malloc, it's being stored in data rather than in a copy, as it was in our previous example. Now let's look quickly at a common mistake. We put this line below the call to malloc. But what if we put it higher, above the malloc call? It avoids having to dereference a variable in a left-hand side expression, which some students find challenging. The types are all okay, and the compiler has no objection. But when we run it, we encounter the same situation as before. Data isn't referring to our new array. Like before, we're creating a local variable, and that local variable gets the return value of malloc, rather than data itself. We can still use a local variable r to access the heap values correctly after data has been updated, but we need to make sure we set the value of data. Finally, before we finish, let's free the memory we dynamically allocated. Where should the free statement go, and what should be the parameter? We should free the memory as soon as we are finished using it. We can't free it before we're finished using it, or we will have a dangling pointer. So it needs to go here in the main function, after the last use of the pointer. Variable data holds the address returned from our malloc call, so this is the parameter we pass to free. In the next video, we will look at allocating space for more complicated data structures.